Hello everyone. This week I'll be posting the videos separated by lesson, so hopefully this will go a little bit better. So let's start with lesson 115 that I wasn't able to finish last week. So I believe we talked about the exponential rules. So we know that 10 squared equal to 10 to the x, therefore 2 equals x. So if we get some slightly more unusual exponents, we can still say that the exponents are equal. All right. We can also use the log functions to simplify or solve problems like this. So that will lead us to get, if we simplify this, to be in terms of 10 to the something, or the log of 10, 17, which is equal to 1.23. We'll see, just like this one up here, it's the exact same equation. We're going to end up with 1.3 equals x plus 2, so therefore x equals negative 0.77. Alright, so let's use that idea to look at some exponential functions. Alright, so here we'd be looking at the equation this equation. This is the simplified model equation, or basically the factors that you're going to use for this equation. So these can be used to represent money, bacteria, electrons, anything that is growing exponentially. So we can look at two equations, such as the amount of 200 at you can see these two equations only differ in the rates here, shown by the t. The t equals time. So we can get the first number by looking at t at 0. So basically, when time was 0 at the beginning, before there was any growth, we're going to get this number. All right? And this equation is going to curve up faster than this one, so it's going to look a little bit like this. It'll be, we'll say this is 200, and it's going to go up like this versus like this. Maybe not, it's definitely not to scale, so just an example of how this one is the 0.2 rate of growth, and this is the 0.4 rate of growth. So 0.4 is going to grow a lot faster than the other one. So we get the, if the constant, this constant, is negative, then our graph will curve down like this. Sort of like that. All right, so let's take a look at some problems. All right, so we have, in the beginning there were 400 bacteria in the dish. The number of bacteria increased exponentially. 3 days later there were 2,000. So how many bacteria would there be in 8 days? All right, so we'll start by writing out that original equation. We have AT equals our amount at T0 EKT. All right, So we've got to find the amount at T0, and we've got to find K to be able to find out how many bacteria would be there in 8 days. All right, so from the problem, we can see that the amount at T0 was 400, so we already have that. And so we can use that to solve for K. So we have 2,000 bacteria after 3 days. We have the original amount, and then we have K, and the time here will be 3 days. All right, so let's divide both sides by 400. All right, and then we use the natural log, the ln, to convert this into a factor of e, or e to a power. And through the exponent rules that we talked about earlier, we know that because the bases are equal, the exponents are equal. So now we can solve for K. Oops, that's a 0. All right, so now since we have K, we also have the initial quantity. We can make our equation for this problem. All right, and we can take a look at the question that was in the original problem. How many bacteria would there be in 8 days? So then we just go ahead and substitute that 8 in for the time and go ahead and solve the equation. All right. So after we multiply that out and simplify that e, we're going to get 29,362 bacteria. All right, so we can also use these exponential equations to talk about money in terms of compounded interest. So, for example, we could say we deposit $100 into an account with an 8% interest rate. So we can look at that account and we can say, okay, so after 1 year, you'll have your original $100 plus your interest. So 8% is times 100. We're going to end up with $108. All right, so then we can say that that's the same thing as our total amount is 100 times 1.08. Now, if we continue this for every continuous year, then we'd end up with an equation something like this. So we get 100 times the interest, and then the next year, we multiply that by the interest, and then the next year, we multiply that by the interest, and so on and so forth. So if we simplify this out, we'll say this is 3 years. So after 3 years, it's the same thing as saying 100 times 1.08 cubed. So if we keep going, we can say after n amount of years, it's going to look pretty similar. All right. So we can also say, write this equation in a slightly different way. We can say the total is going to be the principal times 1 plus the rate to the power of n. So P equals principal which is the original amount of money, and R is the interest rate in decimal form. And obviously N is for the amount of years. All right, so in the exponential form that we used earlier, it would be written as this. All right, so we're not going to derive how we get from here to here. That is something for a future math course. So you don't need to derive it. I'm not going to derive it. We're just going to take it as that equation. All right, let's do a practice problem. So Roger deposited $5,000 in an account with 7.5% interest. How much money does he have after 10 years? So let's start by writing our base equation. Principal rate times time. All right, so we have a principal of $5,000 and a rate of 7.5% interest. So we'd write that as 0.075. All right, so then our equation for this problem would be the amount is 5,000 times E to the rate times time. All right, and we're looking after 10 years. All right, so we'll just stick 10 in there for T, just like that. And we're going to use the inverse log to simplify this out. So our amount after 10 years is going to be 10,600. And that's your answer. All right, that's all for lesson 115. I will continue the next lesson in the next video.